Easy thing. It's print on the screen our parameter. Probably you remember that sometimes we put parameter with brackets, with round brackets, sometimes not. In general, if you have one parameter, you can omit brackets. If you have zero parameter, you should put brackets. If you have more than one parameter, you should put brackets if you would like to define proper lambda lambda function, proper function with lambda syntax. Then in this case, I have omitted brackets. I put a variable. The name is can be different. No one told what kind of name should be. You can define your own name. In this case, because it's loop, I decided to use E, like almost always in for loop. And as you can see, this loop works as many times as shown, as defined in the parameter in the first and second parameters. And on the left side, we have execution result. On top is the serial process. It means that normal for loop. On bottom, we have parallel process. As you can see, number 2 is removed from this place, but is put it later. Something works, something stopped this process, and this process was finished later. It's as I told earlier, it's the evidence that parallelization works. Parallelization works in our execution, and how you should understand it. Again, you have a method defined by delegate. The method accepts one parameter of type of probably integer. I don't remember, but it's number. It's number, and you can do something in your method. In our case, we only print this parameter, and this method will be executed from first parameter to last parameter as many times as difference between second and first parameter given here. Okay. Next one. It's the easiest possibility how you can do it, and you can now imagine that if you made your exercises with integral, with calculation of integral, then you can imagine how you can use it in calculation of integral. Of course, as a as e parameter, it's given step, which was earlier defined in serial linear loop, and you can use parallel for to execute everything in the same time or parallelly. Many tasks you can execute parallelly. Of course, after calculation of square or rectangle area or rectangle or trapezoid area, you have to summarize everything. It's next challenge. We will talk about it, how you can do it, because I will present you a method how you can synchronize many parallel execution. Okay, let's go forward. Second type of loop, it's for each loop. Probably you remember that in C# language, especially in different type of languages, exist for each loop. For each loop executes. Oh, like in this example. Oh, very good that I have it. It's iterate over elements. On the top, we have defined LST list of type data. Type data is defined on the left side. It's the class with the name data, which has two fields. First field is a name, second property is wait time. And on the right side, on the bottom, we have defined the list, and the list is filled with 3 new elements of data. First with wait time 100, second with wait time 50, and the last one, third, with wait time 1. We will use it to make some delay in our process. And run method, it's in this case is start method. Of course, I didn't present a main method of application. Probably in the main method is you can expect that there is an instance of, one moment, because I lost something. There is a definition of instance loop example, and on this instance is executed run method. You can imagine. And our run method prints serial process on the beginning. Next, run serial. Our run serial has for each loop. Our for each loop iterates over LST list elements. As you can see in this definition, we should give a type and name for element in LST. It means in collection. Iterate over elements in collection. Our collection is our list, and we will go step by step. Each element will be processed one by one. In our case, from the elements we take wait time and make delay. Thus delay, it's almost the same what sleep do, but it's written a task. Then we can execute wait on this task. This means that our process is waiting for defined time. And next, our process prints element name process. And as you can see, because our list has first, second, and third element, our elements are printed on the screen, first, second, and third. And next, parallel process is printed, as you can see, and run parallel is executed. But in this case, we used parallel for each. Parallel for each is a method which simulates for each loop with, of course, with assumption that this method will simulate parallel execution of for each loop. In our case, this method accepts two parameters. First one is a collection of elements. Again, in our case, it's a list of 3 elements. And next, we have second parameter with our anonymous method. As you can see. Our method accepts one element. One element is taken from a list. For each element of the list, this method is executed, as you can see. The logic of our method is similar to the previous one. To be fair with rules of good programming rules, I should remove it to the external method and run it from this place and this place to omit the situation in which I copy the code. But of course, we talk about I would like to make it more readable to you, more understandable on this level. Then I don't decided to remove it to second method in general. And second thing, probably it could be problem with a place here. Maybe it will be difficult to put on one slide everything. And then we have 3 processes which will be executed in the same time because it will work parallelly. But you have to remember that first one is waiting the longest, the third one is waiting the shortest time, and middle time is for second second element. As you can see, the result is third is processed as a first element, second is second, and first is last, processed as last, because he he had the longest time to wait, the longest time to wait. Then, as you can see, our execution isn't blocked by previous iteration of our loop. In general, we can treat it as a loop, but of course, it's a simulation. It's more than simulation of loop than a real loop. Okay, okay. Let's go forward. Parallelization level. Parallelization level, it's something which allow you to control how many threads will be executed, will be created in our loop. In our loop. As you can see, we have a version of for each polymorphic version of for each method, which can accept more than one parameter, more than one. It, in our case, is two parameters. First one is similar to the previous example. Last one is similar to the previous example. But the middle parameter in this case, it's something like an options for our for each loop. In our case, we will put an options in which we define max degree of parallelism equal to. It means that our loop for each loop can execute only two threads, no more than two threads. Sometimes it's useful because, for example, if you have the process which is very computing consuming, the computing power consuming, then it could be situation in which your application gets a lot of resources of a server example, and server don't have possibility to process different tasks. And there is a method how you can put a restriction a restriction to your parallel loop in general, because you can tell in your code, you can tell to your parallel loop that you shouldn't use more than 1, 2, 3, 4. 1 is stupid. 2, 4, 3 or more threads. It's useful thing. You should remember about it, that it's possibility, because you can imagine if your process is very power computing consuming, then your server could not have enough power, enough resources to process different tasks outside of your application example. In our case, we have used two threads. Then we can analyze how it works. Of course, serial process works in the same manner like in the previous, nothing special, nothing was changed here, then it's the same. But second, parallel process was changed, because in the previous slide, the order was third, second, first, but on this slide, the order was different: second, third, and first as last one. How it's happened? Because we remember that we can execute only two processes in the same time. It means that first process was started because it's on the beginning on our list. Second process was started because it's the second one, and our for each loop was waiting for the room to execute one more thread. To achieve a room, to obtain room, the previous one should be finished. As you can expect from two, first and second, faster is second, then second was finished first and print on the screen result, element second. Next, last element, third element was executed. his waiting is very, very short, then he finished very fast and print his result on the screen, element thread. And the last one element was as the first one, because his waiting was the longest. And as you can see, the result was changed. The result was changed. The calculation was the same. The logic of our thread was the same, because he would like to wait and print something on the console, but whole result is different, because you can expect that these parallel processes works. Each parallel process lives in his own manner, and if you will make an application which process something in different threads, you should remember about the situation that each thread works in his own life. He lives in his own life, and summarized result can be unexpected. Okay, this was last slide of this presentation, which means that we have to open next one presentation. To use it, I would like to find it. Again, I will take to the second monitor. Which one was? It was 5th. Okay, then now we would like to open 6. Number 6. Number 6. And some slides are duplicated, but only one slide to remind for longer breaks. Our breaks took 30 seconds, then probably I shouldn't repeat everything, and I should determine these slides, and I did it. You can see that you have parallel 4 on the right side. Okay, then partitions in general. Partitions. We can say something like this. Partitions. Partitions is something which allows you to divide your space, calculation space, bigger calculation space, to shorter parts. Of course, as you can imagine, our integral, you can divide a space to very, very short parts. It means each rectangle can be calculated in his own thread. But you can, if you remember that creation of a task is it's expensive in general, then you should understand that better option is to use more rectangle. Better option will be when you will calculate more rectangles in one thread than only one. Example, if you have 1 million of rectangles, then it's good to divide by, I don't know, in groups with 100, 1000 or something like this rectangles, and create for these rectangles you can create a thread. In each thread, it's calculated group of rectangles and similar thing. To do it, we have something which is called partitioner in general. And here is an example. How you can use it on the slide. I am trying to remind what's going on. The result you can see on the right side, that something was happened, something was worked here. And how you can do it. We can use parallel for each with additional with additional data, with additional data in general. Uh, this line produces a space for us, space of data. Probably in real life, these data are taken from, example, database or somewhere. You have group of values which should be divided. Next one creates something which is called partitions. Maybe I should say partitions. It means that our space is divided to parts. In our case, we have 100 elements, 100 elements from 1 to 100. We are creating a space which divides our space, 100 elements to groups, and we are trying to execute. Our code. Mm, Then let's go forward. Uh, first parameter of our for each loop is our orderable partitioner. Partitioner contains groups of elements, we can say. Groups of elements. Next, second parameter is a method. It's an anonymous method in which first element is a tuple which define our space for each iteration of our for loop, because we remember that method is executed many times for different data in general, and the range defines the space. The range is taken by for each from orderable partitioner. It means that partitioner create a tuple for us tuple of type integer. First element is the beginning of our space. Last element is the end of our space. Our group, maybe I should say, because space is from 0 to 99 in this case. The last element is the end of our group, and this tuple from the beginning to end is put to variable range. And we can use it. Start range is how to say, is taken from a source. Our source values start from 1 to 100, and you can imagine, because it's list, you can use it with an indexer. You can put an index of element. In square brackets from our source. The 0 element is equal 1. First element, first index gives us 2, and so on to the last element, which gives us 100. And in this manner, we can choose beginning and to end and at the end of our range. Of course, you could use it, a normal loop to iterate over data from source to make calculation for each variable, for each source element or something like this. And as the last part of our logic, we printed something on the screen. Range execution finished for number of identification of our task in general, with range from start to end. What you can see on the screen. And we have groups, something like groups. 1, 5, example, 97 to 100, and similar thing. Our partitioner makes parts of our execution, what you can see. And very interesting thing, for me, it's interesting that you can see that there are many times task current ID. It's duplicated many times. It's the same task. Example 1 is 1, 2, 3, and so on. It means that optimizer probably decide to use the same task. It gives a possibility that the for each loop or different tools too tries to optimize the solution. If you would try to make it with task, each task will be created in his own space. In the for each loop, the thread can use the same resources. It means that our for each loop don't have to allocate the resources because they are prepared. Only for each loop should reuse it. And partitioning can be faster than execution step by step. Our case from the previous laboratories, integration calculation. If we on the first first presentation first lecture, I showed you that parallel execution isn't as fast as you can expect if the calculation is very short. Then you can make calculation longer because you can use partitioner to get more than one calculation in one thread. Example, you can use many calculations in one thread, but everything is divided to the parts. Then you can use each thread in your processor, each core in your processor. It means that you will use properly the resources. You will use resources in proper manner. Okay. One moment. I will try to open my phone. Oh. Okay. It happened, and I will check how many time we have, because I don't remember. 5 past 3. 5 past 3 we should finish. Okay. Okay, then let's make short break for my health. Oh, I have proposition. I will come back in a few minutes. Okay, I came back. Let's continue. Okay, about partitions we talk, how it works. Let's go forward. Loop break. We have possibility how we can, you remember that in the task example, background worker, we have possibility how we can break a calculation. It's useful function because it isn't, or probably you shouldn't. You should break a process in proper manner. Then background worker has own method how you can do it. In task you can use token. You can use token, cancellation token. And in the breaks, in the loops, you can use parallel loops. In general, you can use break method, stop method, or cancellation, or property, I should say. Break property, stop property, or cancellation token. Example will be given. First one, break, terminates the loop process and lets that the lower iteration will be completed before the loop ends. It means that in one moment you decided that in one moment you can decide that everything is made. Example, if you are looking for something and you decided to use parallel loop, then probably one of iteration will find in one moment the solution will be fine. Then you should probably stop processing. You should break next processing. But example, you would like to allow to finish started processes to finish started calculations, and you can use break property. You can use break property to execute it. Let's analyze an example. I believe that it will be the most useful situation in which we will try to explain what's going on. Okay. First one, the random. New random, class random allow us to generate pseudo-random variables, pseudo-random values. You can treat it as random values in general. Number to find is 5. And there is a variable, constant variable. Constant, it means that it isn't able to change, is created as during a compilation process as a constant in general. It in the application it doesn't have, in the code it doesn't have own name, it's only value. It's changed to a value. And okay, next we have we defined a parallel for class parallel and static method for, which allow us to create to run some method many times from 0 to 99. It means that we will execute it 100 times. And last parameter is an anonymous method. It's anonymous method. And our anonymous method can accept two parameters. In the previous examples, I showed you that it can accept. Oh, I don't have it was in the previous loop. Oh no, it's here. In the previous example, I showed you that it can accept one parameter, but we have polymorphic version of for loop, for parallel for method, which can accept an anonymous method or delegate, in general delegate, with two parameters. First one is E, similar to the previous example. It means that it's number from 0 to 99. And second one is parallel loop state, which is shared between different types, different iterations, between different iterations. And I will try to explain you what's going on here. Now let's go. First, our thread is sleeping 1 second. It simulates a long running process. Next, with a parallel loop state has a property, should exit current iteration. This property will be set to true if somewhere will be executed break method on parallel loop state. If somewhere inside our loop, parallel loop state, it means our options, our parameters given to the method on our parallel loop state will be executed, is break method executed, then should exit current iteration is changed to true. And next, we can check in parallel loop state if our if lowest break iteration is value passed to the method with E variable. Lowest break iteration is different than our current E variable. If it's lowest than our current, it means that we shouldn't execute our code. We shouldn't execute. Our current iteration shouldn't be executed. It means that our parallel for executes iterations of our method. Each iteration has own E value. Inside the code, somewhere inside the code in our method, parallel loop state break will be executed. It means that our iteration found solution or calculate solution, and everything, the next iteration shouldn't be executed. Then, if we execute break method, the lowest break iteration is remembered inside parallel loop state, is equal our current E variable. Then later, in next and in the previous iterations, we can compare if our lowest break iteration is lower than our current iteration. If it's lower, it means that next iteration should be break, should be stopped in general, which is executed with return keyword. If not, we are going forward. Our logic is checking if E is equal to number to find. Number to find is, in this case, is set to 5. Then you can imagine that, you can understand that we have planned to execute 100 iterations, but after first 5, we should stop everything. We should finish only existing, only lower iteration. iteration with a lower E variable. Then let's go forward. If E is equal number to find, it will be in very short time, because I remind you that number to find is equal 5. We print something on the screen. Number 1 was found, breaking the loop. We execute break method on our parallel loop state, and we omit. We left our iteration. Then, as I told earlier, next iteration, if it's executed, checks if should exit the current iteration, should exit only in situation when a break was executed. If our current iteration is lower than, current iteration is greater than iteration on which parallel loop state break was executed, then we will go to return. If not, we will go forward. E isn't equals to number to find, then we will execute our code. It means that only iterations in this logic, only iterations with E lower than 5 will be executed from 0 to 4 or 5 times. What kind of logic is presented here? We have some calculation here. Our some calculation operates on random number, and we print something on the screen. Total from calculation, from task ID given here, iteration E. Then we should see on the screen, 5 lines with information total something presented here. It's a possibility how you can, with the break, you can break an execution. If you found or you decided to not finish, but finish the previous, but you should finish the execution, the iteration with lower, or maybe in other words, iteration started before our 5th iteration. It's all in this subject. Okay, second example with stop. How we can stop. Situation is similar to the previous one. We have parallel 4 from 0 to 99 in general. 99. We have method with 2 parameters. E is from 0 to 99. Parallel loop state is an object which is shared between iterations. And next, we are waiting 1 second to simulate long-running process. Next, we checked if our number to find is equal, if our E is equal number to find. If it is, we print that number was found. We execute stop method over parallel loop object or parallel loop state object, and we left our method. We left our method with return word. Then, if it will be executed different, executed different iteration, then we will check if E is equal number to find. It wasn't. It won't be equal because we analyze the situation in which E is equal number to find. Then we can go forward. And in the next line, in the next if statement, we checked if our parallel loop state is stopped property is set. It will be set only if stop was executed. If stop was executed, we are going to return, and we omit our method tool. If it wasn't, if is stopped is equal 4, it means its iteration was started and executed before the number to find. We will go to our logic. Logic is the same like in the previous example. It's the possibility how you can control the flow and how you can share the information between iterations. If one of iteration will find the solution, if one of iteration find the solution which is calculated, you can break everything, or you can allow to finish previous iterations but stop to execute the next iteration, the future iteration, which will be executed by parallel for loop. It's, I think, very useful tool. And last one possibility with cancellation token source. And general cancellation token, you know how it works, because we had exercises, we had examples. I don't remember if we had yes, we had exercises, because our last laboratory, you should make termination of our thread too, like in the background worker. Okay, let's go. Cancellation token is declared. Cancellation token source is declared because we would like to use it later. Next, in the method run, first we started a task. Task is waiting 5 seconds. And next, executed method cancel on cancellation token source. You remember that after the execution cancel method on cancellation token source, something happens, some kind of properties is or are changed. Next one. We define parallel options object and set cancellation token to our token taken from cancellation token source. It means that we maybe in different word. We prepare an object which will be passed to parallel form. Object with configurations. Object which is called parallel options tell us that the name tell us that there are some kind of options to configure our parallel form method. And the next one. If we will go to our parallel form, we can see that we will execute from 0 to the max value of integer 32. It's big number in general. It's big number. If you would like to check, you can find on the internet a table with types in C# language. And third parameter is loop options, and last parameter is a method. As you can see, our method is waiting 3 seconds. I remind you that our code is waiting 5 seconds before cancel our cancellation token source. In our method, our parallel method is waiting 3 seconds and print something on the screen. Calculation at index and given index. I forgot about E here, but it doesn't change. It changed nothing. Then probably you will forgive me this small mistake. And how it works. Or maybe I should tell one more thing. If we'll use cancellation token, exception, operation cancelled exception will be thrown. Then you have to remember that you should catch everything in try catch. Oh, I will finish on it. I will put a dot. As you can see, if we catch an exception operation cancelled exception, we print on the screen information that cancellation exception was caught. Or cough, I should say cough. Okay, let's try to analyze execution. We can see that we have many or few executions. Calculation and index. It means that our parallel for executes many operations. Index is taken from 0 to max value. That you can see that we can 1, 0, 2, 4, and bigger numbers too. It means that our computer, our operating systems decide to run different threads with different indexes, different iterations without ascending or descending order. It looks like random iterations. But after 2 seconds, of from printing and 5 seconds from starting our process, cancellation token source cancel method is executed, is obtained by the first task defined here. And from the time when cancel method was executed, we have passed cancellation tokens. We have passed token in general from cancellation token source to our parallel for. We have passed it. Then our for method breaks execution. And as you can see, in one moment, token has been cancelled, is executed because it's the text is printed on the screen. Few seconds later, or few moments later, few milliseconds later, we have on the screen information that more iteration is executed, but and on the final we have information that cancellation exception code cancellation exception code. It means that token was fired, cancellation token was fired, cancel method was executed, and the processes started to break our for loop, and our for loop was stopped. But of course, few moments later, because the probably started threads had to be finished. But there is a possibility how you can, probably in its easiest manner, how you can break an execution. Of course, the result is an operation cancelled exception, but exception can be catched by our code that nothing strange happened in this code. It's possibility how you can control of our logic. Okay, let's go to the next subject, to the next slide. Probably it's last slide in this subject, because the next slide will talk about something else. Sharing, variable sharing. We have possibility how we can, or maybe in another way, possibility to share variable between iteration. It probably can be useful to calculate something. Then allow me to explain you how it works. 1, 2, 3. I see three parameters. By not 3, 5 parameters, but opposite to the previous examples, we have 3 given as a delegate, as a lambda expression. First 2 parameters, there are begin and end of our of our loop, the first element and almost last, almost because our execution will be made to 99, not to 100. Next parameter, I remind you that polymorphism exists inside in the C# language. Then you can have the same method with the same name with different types of parameters. Compiler is able to detect what kind of method should be used because the parameters has different types and no number of parameters can be changed and types of parameters can be changed. Then in our case, it's beginning and end of the range. Third parameter is an initialization of our shared variable. Our shared variable. In our case, shared variable is subtotal. Subtotal is the variable which is shared between iterations. Next one is our method, calculation method. As you can see, our method accept j as index in general taken from 1 to 99. Variable loop, I don't remember, probably it's something which was presented earlier, like parallel loop state, which isn't used here. We don't use our loop object, but we have additional parameter called subtotal. Our subtotal is a variable which is shared between different iteration of our method. Then our logic is very easy. We take subtotal which comes from outside. We make some calculations on our we make some calculations, so execution, and assign new value to our subtotal variable, and we return the value in general. The returned value will be passed to the next iteration, to different iteration, and it works like I don't know how to say, like a loop. In one thread, everything is passed from one iteration to second iteration, from one iteration to second iteration. Then we can summarize example values. Yes, we can summarize values during execution. Like in this case, we take a value from the previous calculation, we calculate something and return recalculated value, which is passed to the next iteration. And it works in this manner. But of course, we have one more parameter. Which is executed for each partition. We can say something like this, which partition, because our iteration works in one thread. How to say? In one thread can be many iterations can be executed in one thread, but after some iterations, the result of our iteration is returned, and the result is passed to the last method, given as given with lambda syntax. And calculated subtotal is passed to our task variable, and we print something on the screen. We have used interlocked add method. I will explain you if we will have time. We have only 5 minutes, then probably not. I will explain it in the next presentation. What's going on in this line, but you have to know that result from iteration in our task are taken with a last method. Our last method can do something with our result, and it's all in general. And as you can see, we have 1, 2, 3, 4, 5, 6, 7 iteration. Now we have more iteration, maybe 10. Here we have 5. The optimizer decides how many threads it should be executed, how many threads. But each thread is divided to the parts. Each thread is divided to the parts. It's something like partitioning presented earlier. And some number of iteration is made, and the result from some number of iterations is passed to the last method. And as you can see, different solutions are presented, different execution are presented, but total sum equals is always the same. Total sum, you can understand it as summarize sum of numbers is sum of each iteration from task result. If you will calculate these numbers, and these numbers, you will always receive 950 always, because our for loop parallel for divides the space from 1 to 99 to the parts. Each part is executed in own thread. Own thread has own result, and result from each thread is summarized to sum of numbers, which is presented as a final number. Then you have possibility how it's possible to execute to divide data to the parts and did on this data the same operations because each j variable will be executed in the same manner. Result can be different because each task, each thread can gives us, each execution can gives us different number of threads, different combinations of threads, different results, but summarized result from each execution always should be the same if the execution is made in proper way. Okay, next presentation will be about thread synchronization. We will explain interlocked add method, how it works. Many more methods we will explain how it works, how you can synchronize information between thread, task, and similar things, how you can use it. On the first presentation, on the first lecture, I showed you that you can do it with some method. I don't remember which method was used. I don't remember. It isn't important, but of course you have to know that synchronization, the result from synchronization is the decreasing of efficiency, because one thread should wait for second thread and something like this. Okay, for today, it's all. It's Friday. We should probably you finish your classes with now. For today, I wish you good weekend, and please try to make our exercises. Please remember that you have exercises to do. Of course, the events and parties are important, but you are students and you should learn, you should build your experience. Experience you can build with exercises. Okay, thank you. Someone would like to tell us something, I see, because he has hand up. No?
Yes, I typed something in the chat.
I don't know. You can say us.
I was asking how many lectures are left.
I don't remember, but maybe 4, maybe 5, something like this. Why do you ask me about it?
So we can start getting ready for, end of semester, if there's an exam.
I believe that you can check the timeline in the system, in the virtual Dean's office. You can do it. You don't ask me. You don't have to ask me. You can check and tell everyone. Me too. Me too.
Okay.
Okay. If you
Hello,
will
sir.
know, please tell us.
Hello, sir. I'd like to mark my attendance.
I don't see you. I don't like if someone talk to me and try to hide
What I
his
did,
face.
I forgot to turn the camera on.
Your colleague did the same. Okay, I can check. Do you remember what I told about? What did I told?
Sorry, sir.
Example. What I explained? What did I explain during presentation? Mister, where are you? I'm surprised, really. I'm surprised. Because I thought that no. One moment, because I thought that colleague want to have an attendance, but I wasn't able to write an attendance. Okay, Mr. Wisdom.
Yes, sir. Yeah, I remember I sent you an email. I just
Oh, really?
Yeah, I just checked my
I-
email. I sent you an email. But
I-
the problem I'm having, I've also related the information to the school admission center. They are yet to update the basic programming course on my model platform. So I cannot take the courses without them being on my model platform.
But I think that it isn't only about the platform. I
Okay.
think that it's more important that you didn't you wasn't present during our classes with basic of programmings.
Yeah, that is where I'm having the issue. I got the information from by email, and I tried to also contact you by email, which I
Mister,
didn't.
I don't know why did you decide to waste my private time? We have classes, and you could ask me during our classes about it, during our laboratories example. Everyone's have time, me too, and I don't know why you decided to send email. But you send, then it happened. We can change it. Okay, how I can help you?
I want to know how to be able to pass the course and also the laboratories.
You to pass a basic of programming are
Right.
two possibilities because you are on the third year currently. Yes.
Yeah.
You can show me that you know how to make programs. You can show me that you know how to that you know the basics of programming. Example, you can show me your previous works, you can show me your previous application, and we can talk about it. Second possibility is that you should be present during our classes. You should make exercises, you should be present on laboratories and so on. Then I'm surprised that you remind in the half of semester that, oh, I should make something.
Yeah, that is basically when I got the notification. I'm a transfer student from Ukraine, so when I got the notification and I have to take your class, that is basically when I texted you. I never knew you were the person who was taking the exact class, so that was why I sent you an email.
Again, we have classes in the school, we have laboratories in the when I don't remember. You could ask me about it in the school. You shouldn't text me or you shouldn't write an email because you have to remember that I have a lot of students and I have private time too. Do you understand?
Yeah, I understand you, sir. What I'm trying to express is I'm a new student to the university, so I never knew you were the one who is taking the classes.
What again? Please
I
repeat.
I am a new student in the university. I transferred from Ukraine. So I've never had a classes with you before, so I never knew your name.
But
So this is the first this
okay, one
so
moment, one moment, one moment. I'm going to the attendance list of our classes,
yeah.
of our laboratory, and I see that first time he met 1 month ago.
Yeah, that is what I'm saying. When I got the notification from the school management, that is when I texted. When I got the notification, I'm supposed to take your class. I got the notification, I'm supposed to take your class, and I texted you about it. And I also texted the school management.
Mister, again, I repeat to you that we have meetings. You don't have to write me text or you don't have to send emails or messages or something like this. We can talk about it. Yes?
Oh, okay, sir.
Because during if you are trying to make something via email, it means that you waste my private time. Do you understand?
Yeah, I understand.
We have during our laboratories, I'm waiting for your questions, from your colleagues. You resigned from this possibility. You decided to ask during my private time, not during time when I'm for you. I'm for you during our laboratories. Do you understand?
I understand you, sir. I understand you
Oh,
completely.
very good, very good. Then we can talk about it during laboratories. But now we should talk about it during laboratories. But now I would like to ask you how I can help you now.
I don't know the days for the classes for the basic programming because it's not on my timetable. So that is the challenges I'm having. I don't know the days for the classes.
Then how can I help you? What I have to do to help you?
I don't know if there are laboratories that have been taking on the classes that I need to take to be able to meet up or to the criteria to pass the course. The course. I don't know if I can get an information on how to go about it.
How to go to classes? You need an information or what?
Yes, the days for the classes, the days for the laboratory classes. I don't know. It's not on my timetable. I've requested for information about that, but I've not received anything yet.
If you would like when classes when the laboratories lectures are, you can check my timeline in the Dean's office, virtual Dean's office. Are you able to check it?
Yes.
Then you can check it. You will know when you should be on our classes from basic programming. Yes.
All right.
And in general, it's all. Do you have some kind of experience in programming or not?
A little bit.
What does it mean?
Uh, minimum average.
What kind of language?
Python.
Only?
Yes, sir.
Uh, Please come to the next class, to the next laboratories. We will think what to do with this.
All right, sir. Thank you very much.
Thank you. Okay. See you. Have a nice weekend.